Hi, I'm Dr. Tom Calabrese, and welcome to this edition of Insights into Computer Science. In this week's installment, we'll be looking into the problem-solving process that I prefer when designing algorithms. Before we start, it would be a good idea to review. Remember in our first installment, we discussed the idea of creating specifications using a criteria and constraint chart? If you don't, now would be a really good time to go back and look at that video again. As I mentioned in that edition, specifying the problem is perhaps the most important of the steps in the problem-solving process. I feel that way because while actually solving the problem using steps 2 through 8 of the method I'll show you today, representing the bulk of the work, step 1, the specification of the problem, ensures that we solve the right problem with the right constraints. Of course, if you search around, you will find a considerable number of methods for solving problems. Every designer and computer scientist will put their own spin on things. But the method I plan to show you today is a time-proven method that really helps the designer to produce a quality project based on strong consideration of available technology and existing algorithms, along with high-quality documentation to support the work. This method that we will review today has 8 steps. Step 1, specification. Step 2, data gathering. Step 3, a pen and paper analysis. Step 4 is design using a top-down approach supported by flowcharts, pseudocode, or finite state diagrams. Step 5, writing code. Step 6, testing, planning, and execution. Step 7 is documentation, and step 8 is generalization. An interesting note that you should keep in mind is that as you master these steps and gain more experience both as a designer and with coding, you should start to see that you will spend about 60% of your time on steps 1 through 4 of the process. That is, planning and thinking. 15 to 20% of your time coding, and the balance of the time on steps 6, 7, and 8. I've been doing this a long time, and one of the things I notice with students is that there's a really strong tendency to start coding right away without following the process outlined here. This will tend to cause you to make a lot of mistakes, both syntactical and worse, logical. A better idea is to get in the habit of following a design process that emphasizes planning and thinking. This will minimize mistakes and help you to make sure that the logical portion of your design works before you start to write code. Not to minimize the coding phase of design, but really coding is just a tool. Now, it's an important tool, but as you grow in experience, you will see that learning different programming languages is a relatively easy task, and that each language offers something to take advantage of in the right situation. Therefore, it's important to build up a good working knowledge of lots of different programming languages, but no programming language represents the magical silver bullet that can solve all of your programming problems. Think of it this way. If you were an architect designing houses, you would be concerned with things like strength of materials, stress points, soundness of the foundation, drainage, structural soundness, material selection, positioning of the building on a property site, well, septic, soil composition, the effects of wind, rain, and generally exposure to the elements. You might not really care all that much about which type of hammer or saw a craftsman chooses to accomplish his or her task. It is something you would know about, but not something you would spend a lot of time on, even though there are many different hammers and saws to choose from. This is something that the craftsperson would spend time on, not the lead architect. The same is true here. Coding techniques and programming languages and different computer hardware are our tools, and someone does need to worry about them later in the process. What's the point? Think before you do. So learn and follow the process. Okay, so let's learn through example. Suppose that I were asked to create a working program that can compute factorials. Remember from our previous lesson that what seems straightforward may not really be so. To a mathematician, a factorial is a relatively useful and straightforward thing. But for most regular folks, we need to understand a little more. A factorial means that we take a number and multiply that number times all of the preceding numbers down to 1. So 5 factorial, written as 5 exclamation point, is the product of 5 times 4 times 3 times 2 times 1, or 120. Okay, that seems easy, right? Well, let's see. Step 1 says, let's take a look at the specification. What are the criteria? Well, to compute x factorial, we need to first get a number x from the user. So the first criteria is to input and assign a number to the variable x. Next, we're going to want to print out our answer as a power of 10. Why? Well, you see that factorials get big very fast, and powers of 10 make expressing that answer more precise. How about some constraints? Well, the first one is that you will see through experimentation, our factorial program has a very large answer to deal with. For example, 12 factorial is 479,001,600. Why is that so interesting, you might ask? Well, that is the largest factorial that fits in a signed long word, meaning one bit holds the sign, positive or negative, and the other 31 bits hold the answer, the number itself. So our constraint might be to use a signed long word for the answer and error check the input to make sure that the user does not ask for anything larger than 12 factorial. That seems low, but it does give us an understanding of how powerful factorials are. Other constraints might be to perform only one calculation per run, since the user didn't ask for any more than that. Personally, I would look for clarification on that from the user. We might also decide to round our answer to 4 significant digits after the decimal point. Again, this is something you have to clarify with the user. Now, we'll come back to this step in a minute because our process is iterative, meaning that we will take a step, discover some new stuff, then go back and fill in the previous steps with more clarification. In step 2, our data gathering step, we try to ask and answer questions that factor into our design. In this case, we might want to know how to convert a number to powers of 10. Well, if we do a little research, we can see that we may want to create a simple algorithm that divides the answer by 10 iteratively until the new dividend is less than 10, and the power of 10 is represented by the count of that loop. Another useful question may be to further explore the largest factorial we can compute and what size variable to hold it in. It turns out that if we try this in MATLAB, which is a very powerful math tool that runs on Intel-based systems, we can see that 170 factorial is the largest that it can compute, producing an answer of 7.257415615307994 times e to the 306th power, using a 64-bit unsigned integer. Of course, this is hardware dependent, but it is still relatively small from a factorial point of view. But it is much better than the 12 factorial we were going to get before. Finally, there are other ways of looking at how factorials can be calculated, so we want to explore those. First might be straightforward multiplication. Second, we can simply look them up in a table since there are so few of them and they don't change. Finally, we could use a method known as recursion to compute them. Notice how this changes our step 1 chart. This, in a real example, may lead to more data gathering and more revision and so on. In this case, let's say we decide to use the 64-bit implementation, 4 decimal point precision, powers of 10, but are not sure about which method to go with. To address this, we need to go to step 3 in our process, the paper and pencil analysis. I like the name of this step because it reminds me a lot of how I used to do things when I was getting my first computer science degree in 1980. Back then, computer resources, access to the computer, were scarce. So unlike today where you can just try things, we had the added problem of not wanting to waste runs on the computer. This means that we had to do a lot of things on paper first. Remember, think before you do. In this case, we could see that the straight-up multiplication can be done in a loop counting backwards until we get to 1, and then returning the result. Recursion is a much more interesting process as it takes advantage of the natural power of the stack in the operating system and results in a simple function that calls itself over and over until the result is known. When the function reaches what is known as the trivial state, that is the factorial of 1, which equals 1, then it can unwind and continually return the answer to this reductive problem until it returns the final answer to the original calling statement. This sounds confusing. Well, we're going to leave that for another lesson in the future. But trust me, it works. Finally, we can simply search a table. Now that seems relatively straightforward, and we can see that it would certainly be the fastest. But since we were specifically asked to compute the answer, we will choose the straightforward multiplication method, as that seems to be least complicated and most in line with what the user asked for. Again, we could go back and redo the previous steps accounting for these new improvements. So take a look at what the constraints and criteria chart looks like now. On to step 4, the design. Design is an interesting step. At this point, you have a real feel for the problem and the answer to most of the questions you had as you were exploring the problem space. You also have your paper and pencil analysis complete with an example or so, and the design seems to be within our grasp. Now, design is really a communication process between the computer scientist and the person who does the programming, even if you are both the designer and the coder when working in the small. In a production environment, you are usually communicating your design to teams of people who need very specific instructions. To make this communication more effective, we'll do several things. First, we're going to use a top-down philosophy. The top-down orientation is important as it allows us to break our problem down as we solve it. To do this, we're going to use IPO drawings, or input, process, output diagrams. In well-written code, the main program, say in the C programming language, for example, would contain some minimal control logic. Let's say a control loop to repeatedly ask the user for a new number to factorialize, along with a series of functions to accomplish the main goal or criteria of the program. Each function is represented during the design phase as an IPO diagram. For example, the IPO diagrams in this case might look like this. Notice that we have 5 of these IPOs, 1 for input, 1 to check the range of data, 1 to compute the factorial itself, 1 to create the power of 10, and 1 to print the answer. Once this is done, it is easy to see the problem decomposition down to the functional elements. Also notice how the output of one process is used as the input to the next. This connectedness helps us to realize that our thinking is complete. If we had missed something, we might notice a missing input or an unused output. Second, we will choose a communication language, if you will. Not a programming language, rather a way of expressing our ideas. Those are either flowcharts, pseudocode, or finite state diagrams. We can use flowcharts or symbolic representations of ideas. In this case, the flowchart for this program might look like these. Notice all of the discrete steps that show every action, test, function call, I/O statement, etc. Learning the symbols is a relatively easy process, a topic that we'll discuss at another time. An alternative would be to use pseudocode. Pseudocode is not a programming language, but it looks an awful lot like one, with some English mixed in for clarity. So instead of a for loop counting backwards from x to 1, we might say, repeat the following x times, counting in variable I from x to 1. New product equals old product times I, stop. Lastly, we could use a concept known as the finite state diagram. This is really used for complex systems like those found in client-server computing and will be addressed in a later edition. A little too complicated for the problem we have at hand today. Third, we will either use and reference things that already exist. No need to reinvent the wheel. Those things include objects, functions from libraries, functions that we create ourselves, further sticking with this concept of top-down design. In this case, there are already factorial functions that someone would choose, but since this is simply an example, we will pretend that they do not exist. But things like print or scanf in Python input are very important functions that we're going to want to take advantage of. After the thinking part, that is steps 1 through 4, is done, the rest is relatively straightforward. Step 5, coding. This phase is where we'll use our tools, the programming languages, the monitors, debuggers, libraries, objects, computers, simulators, and our networks to build that which we just designed. A key aspect of coding is to work in small chunks. Stick with the design and give out coding projects as per the IPOs. These things can be then written as functions. Don't try to do too much at once lest you overcomplicate the process. Remember, slow and steady wins the race. A personal thing I like to do is to start my code by first putting in all the comments or lines of code that are ignored by the computer and are just there to make reading the code easier. I love to comment code. This will make the documentation process and the testing process easier later in the future steps. The comments should match the flowcharts and illustrate the flow of the code or special conditions that you need to include in the code, describe library functions or custom functions that you create, especially what the input to and output from those functions should be. The more comments, the better. Once that is done, go back and write the code to match the comments, and you will see how easy this really is. Step 6, testing. Testing is the step that is far too often minimized. Testing can be very complex and a topic that we'll discuss at another time. But think of this. Your Microsoft operating system has upwards of 30 million lines of code in it. The planning and writing of it was hard enough, but how can you test out that many lines of code and who knows how many logic paths through that code? Testing like this is done at many different levels. At the function level, the unit level, the program level, the system level, the user level as either alpha or beta testing, and as part of remediation is necessary. In this case, we'll see that all of the testing of our constraints along with the normal operation would be important. What happens if I input a negative number to factorialize? What happens if the number is too large? What happens if I change to a more powerful machine that allows me a greater bandwidth? This is so important that whole textbooks have been dedicated to it. Step 7, documentation. The documenting of a project is relatively easy if the comments in the code and the specification of the project have been done well. It is important to expand on these items to allow for the creation of a user document that includes an installation and startup guide, a troubleshooting guide, and more technical manuals as dictated by the project or product. It is also necessary to take all of the steps in this process that we've done so far and create a precise engineering set of documents that can be used to preserve and troubleshoot the project or improve the product down the line. These documents would include all 8 steps and would often include the results of test data, graphic design, and user feedback. Step 8, generalization. The final step of the process is generalization. What we want to accomplish in this step is the re-examination of our work to see if we met the original criteria. And we also want to look at what we may have created or potentially could create down the road from the product that we just made. For example, how might our factorial program be used inside another program? Or can our powers of 10 code be useful somewhere else? Or can we make other programs like a general purpose calculator out of the program we just created? It is important, especially in large contexts, for the project team to reflect and then generalize to see if there are any undiscovered benefits from our original project. You would be amazed at how often this yields some beneficial results. As you can see, our initial project of producing a factorial had many twists and turns. We were able to identify interesting niches that could affect the proper use and operation of our program. Most important, you can see that it is important for computer scientists to follow a process and make use of that process as part of their normal operating procedure for design. Until next time,